common alkene reaction that we use a lot in organic chemistry is one that forms an epoxide. An epoxide is a really nice and reactive compound that we can use to make all sorts of other things, and you'll quickly see why. So to first review, I will tell you that the epoxide is very similar to the brominium ion that we've been forming. So as you remember, when you have an alkene of some sort, and that alkene attacks a Br, this Br has a very strained bond, as we remember. Okay, has a very strained bond right here. This bond would love to break. Now, why would that bond love to break? Well, bromine's really electronegative and it's really pulling hard on that. So as that bond breaks, what we're going to have is this Br breaking as this arrow comes and pushes these electrons to that Br. At the same time, we're forming a really positive carbon here, which allows those electrons to attack the other carbon, forming this very, very reactive intermediate. Why is it reactive? Well, because the bromine has two bonds, so it has a positive charge, and it's so electronegative that really that positive charge is mostly residing on these two carbons as strong partial positives, which can then be backside attacked. To review the backside attack, remember that these bonds right here are sigma orbitals. But if there's a sigma orbital, there must also be a sigma star, which is an antibonding orbital. That antibonding orbital is empty, but exists right here on this carbon and bromine. Well, this antibonding orbital is on the back side here and is the perfect place for this other Br negative that we just made in the last reaction to put its electrons in there, breaking this sigma bond and forming a new bond. Remember, this is called anti-addition. So that's some review of how bromine forms this brominium ion right here, this three-membered ring that's quite positive, that's perfectly set up for a backside attack to create some anti-addition here. All right, so now let's dive into epoxides and how epoxides are formed in actually a really similar way. So, MCBPA is one of the compounds that we frequently use for this. Now, MCBPA, I'll break down the name really briefly, but we'll get into this later on in organic chemistry. M stands for meta, because if you're looking at a benzene ring, and this is called a benzene, when we have a six-membered ring with those alternating double bonds. On a benzene ring, if we're talking about some main compound, across from it is para, but right here, this position is next to it is ortho, meaning that in between is meta. That's what in between means. So this is meta, that's what that means. Meta-chloro, right? C is for the chloro. Benzo for benzene. Peroxyacid. Now this is the important part that I want to break down here. This stands for peroxyacid. Now, peroxy comes from peroxide. And if you know what hydrogen peroxide looks like, hydrogen peroxide looks like this. It's hydrogen peroxide. And it has a peroxide bond, right? This is literally called peroxide right here. So hydrogen peroxide is when we put hydrogens on that peroxide. And a peroxide bond like this is a very, very, very weak bond. Hydrogen peroxide is really good at oxidizing things because this bond is so weak that it will break easily and form all sorts of very interesting things that it's a lot of times it can even form oxide radicals, right? So this peroxide is right here, and a lot of times we refer to everything else here as R, an R group or representative group. So the way that this can be redrawn oftentimes is we can basically just take this whole thing and get rid of everything over here. And just say R, because R refers to all that other stuff. Now, why do we do that? Because the peroxyacid, which is this part, is the part that's actually going to be reacting or reactive. So let's bring our peroxyacid over here now and look at how it actually reacts. Well, peroxyacids, and I'll go ahead and label this here as our peroxyacid. Peroxyacids, as I said, have a peroxide bond. Now, this bond right here, I'll go ahead and make blue. This is our peroxide bond. Sorry, I draw it better here. And that peroxide bond is really, really weak. Why? Because the oxygens are very electronegative, so they're pulling really hard on those electrons. Also, don't forget, we have some resonance up here. Remember that right here we have a carbonyl, and we're really used to the fact that carbonyls form this resonance pattern, where we have the electrons going up, making an oxide with this negative charge, but also at the same time leaving a positive charge behind on that carbon. Well, that positive charge means that that oxygen over here that's already really pulling electrons now is next to this partial positive carbon is going to be pulling electrons even more, right? So this bond is very weak, and we have that partial positive and partial negative here. Another thing to bear in mind, if we just looked at a carboxylic acid, for example, is that as this happens, a lot of times this carbonyl or the electrons, when they're up in this state, can go grab an acid. So a lot of times what we can end up having is that become protonated. Now that's also going to play a role here. All right, so let's just look at that really quickly. As that is sort of rotating around here, we also have an OH right here. Now you remember OHs can hydrogen bond. And you see how if there was something happening between these two right here, that could be thought, that hydrogen bond could actually almost make a 5-membered ring there. So we see that that could happen. So let's go ahead and put an alkene in here and see what it's going to do. Now, that alkene, if we put an alkene in here, which is going to be the thing that's going to react, let's say an alkene wanders over right here. Well, what's that alkene going to do? Well, we already noticed we have this resonance. We notice where we have these electrons moving over here. So really what is going to happen at this point, get rid of that arrow to show you sort of how all of this happens at once. You're going to have this bond, peroxy bond, really wanting to break. So that bond is going to start to break right here in this direction. And as that bond starts to break, it's moving over to form a new carbonyl, right? Because we have a p orbital on that carbon that's able to be filled. But as it fills that p orbital, that's happening because these electrons from this partial negative, really that p orbital up there is attracting them. And so what's going to happen there is these electrons are able to move up and grab the hydrogen that they're already attracting, right? Because they are already attracting that hydrogen. Now, as you can sort of see that molecule, that peroxyacid, decaying or falling apart, what's really driving this process and what finishes it off is the fact that this alkene is going to actually attack this oxygen. But as that attacks the oxygen, you notice that we have space here. We have space here because the electrons and that bond are breaking in that peroxy bond. Now, as that bond breaks and the other one attacks, you notice we have some kind of marooned electrons here, right? Because we're grabbing that hydrogen with the carbonyl. What's happening to these electrons? Well, remember with alkenes, every time when we start to use an alkene to attack something, it's really like a door swinging open. Those electrons are remaining attached to one of these carbons, let's say this one, right? So as the electrons from here are attacking the oxygen, they're still attached to that carbon. They're just leaving those electrons are leaving this carbon. So what does that do? That makes this carbon become really positive. And as it's becoming positive, and we have these electrons over here that are marooned, so to say, those electrons are going to attack that carbon. So now you see we've shown where every electron can go and the reason why each of these electrons goes to those places. Well, this is a great mechanism practice for us because it will allow us to show how these curved arrows really play out again. So we have R, and now we need to show a bond where each arrow was, right? So we have this carbon attached to this oxygen, but remember, arrow number 1 here formed a new bond to this hydrogen, which is now here, okay? Now at the same time, arrow number 2, we still have this carbon attached to an oxygen down here, right? And that oxygen had 2 lone pairs, but arrow number 2 formed a carbonyl right here, all right? Now at the same time that that happened, we have these other 2 arrows over here on this alkene. So let's show what happened there. So we have broken that alkene, but we now have arrows number, so let's see, we have 1 here, we have 2 here, and we need to account for arrows numbers 3 and 4, and we'll see that both 3 and 4 formed a bond to this oxygen from the peroxyacid that's now over here, and it still has its 2 lone pairs. Now this, we finally have arrived at it, ladies and gentlemen. This is our epoxide, right? This is an epoxide. An epoxide is something that has a 3-membered ring with 2 carbons and an oxygen. Now, what makes an epoxide so incredible is that just like the brominium ion, this is a ring that really doesn't want to stay like this. It would love to break, but it's not charged like the brominium ion. However, that oxygen is very electronegative, so it's really pulling those electrons. How peroxyacids tend to react, or these epoxides in the end tend to react. Let's go ahead and bring down our epoxide and talk about how it tends to react. And let's go ahead and just make it all the same color. All right, so how we tend to react these is we actually tend to use an acid catalyst or an acid. Why? Because if we have an acid around, we'll just do, I know it's normally hydronium in solution, but I'll just say an H+, is if this lone pair right here attacks that hydronium ion, what we're going to end up with is a hydrogen right here forming a positive charge. So this epoxide is now positively charged, and that's really because that oxygen is so electronegative, means it's going to pull electrons really strongly and form dipoles on both of these bonds. That means both of these carbons are very partial positive. You're now noticing this is exactly like the brominium we talked about earlier. And just like the brominium, let's say if we have a water present, that water is going to be able to backside attack here, because remember, just like the brominium ion, we actually have a sigma bonding orbital right here. This is a sigma bonding orbital. But we also have a sigma star or anti-bonding orbital that has a lot of empty space right here. And this water can use its electrons, donate them into the anti-bonding orbital, thereby breaking this sigma bonding orbital, right? Which would open up in this direction. What would that yield? Well, as we can see, that would yield, looking right here, that would yield an alcohol right here, and that water that attacked, once it's deprotonated, would also, because right, it would at first look like this with a positive charge. We would end up deprotonating one of those hydrogens, and we would get a diol or two alcohols. Now, what kind of addition would this be? We know that this would be anti-addition, because the alcohol would backside attack or attack this anti-bonding orbital that's in the back or opposite of that oxygen. So that is how epoxides can be used to make things. We can attack with plenty of other things, not just water, but we can always use a nucleophile to backside attack there and open that epoxide up. So epoxides can be made in the way that we just explained here, but can also be broken or used to make other things by backside attacking once we've formed the epoxide in question.